Right, we're going to look at some more matrix transformations in this video, but in 3 dimensions. So we're looking when we've got an x-axis, a y-axis, and a z-axis. Okay, so we're in 3D space here. First up, we're going to look at the matrix A, 0, 0, 0b, 0, 0, 0, c. And this matrix would give an A stretch in X, B stretch in Y, and a C stretch in Z. And when I say an A stretch, B stretch, a C stretch, I mean a stretch by scale factor A, B and C, and in X is in the direction of the x-axis. So say A was 2, every point on here of its x value doubled. Okay, just note, special case, if A equals B equals C equals some other constant K, we call this an enlargement. By scale factor K. Okay, so that's us done with stretches. Now I'm going to look at some rotations. Got a matrix 1, 0, 0, 0, cos theta minus sine theta, 0, sine theta cos theta, and this gives us a rotation in X, so we'll just call this Rx, and the rotation is anti-clockwise. Okay, so that means basically if we take our view of the shape from this x-axis, so looking into the x-axis towards the origin, so along this line, then the shape's going to appear to rotate theta degrees anti-clockwise. Okay, sorry about that. Now we're going to find the equivalent Ry and Rz. So Ry would be cos theta 0, sine theta 0, 1, 0, minus sine theta 0, cos theta. And if you notice in the pattern here, it's the x coordinate here that we sort of fix as 1, and then we put zeros in its diagonal, and then we get these almost 2 by 2 matrices within our 3 by 3 matrix, which are very similar to our 2-dimensional rotation matrices, which makes sense because essentially what we're doing is to rotate around one of the axes, we're fixing that axis and then considering a rotation in a 2-dimensional plane. Right, so Rz is very similar. We get cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. Okay, and both of these are anti-clockwise too. Finally, we're yet to define the determinant of a matrix, but we will look at that soon, and I have done a video on in the past if you want to check that out. But just to introduce an idea, and then almost ignore this for now, and then when we introduce the determinant, you've already had some motivation of this. We can define a quantity of a matrix, just a number that we calculate in a particular way, and this number, again, if we've got a matrix A, we denote it either as det A, this, or det A, and they're equivalent to each other. I'll just write one equal sign anyway. Yeah, so that's the notation, and this determinant, this number, gives us the volume scaling factor of a transformation. So if we calculate the determinant of these rotation matrices, and again you'll find out how to do this, but the determinant of Rx, for example, just comes out to be 1, which makes sense. If we rotate a shape, it keeps exactly the same volume. Okay, and yeah, as I say, we'll take a look at how to calculate the determinant in future videos. The next video is going to be on invariant point and invariant lines, and so if you want to find out what those are, be sure to check that out, and it's very closely related to these transformations, hence why we introduce these first. But that's it for this video. If you did enjoy, please like and subscribe, and I hope to see you in the next one.